Welcome to our quantum deep dive. Today, we're taking a look beyond just the headlines of quantum technology. We want to uncover the really profound influence of a key figure in the field, Dr. Debbie Leung. Now, her name might not be instantly familiar to everyone, but as we'll explore, drawing from Yorgo Schneepot's insightful essay, her foundational work is actually underpinning so much of what's exciting and, well, frankly, revolutionary in the quantum world today.
Yeah, quantum technology really is pushing boundaries, isn't it? It's moving past what classical physics allows, opening up incredible new possibilities. And, to really get a handle on its potential, you need to understand the people behind it. Debbie Leung is definitely one of those people. What's so compelling, I think, is how she manages this amazing blend of, deep theoretical insight and very practical application. She makes the abstract concrete, really setting the stage for the quantum systems we're seeing develop.
Okay, so let's unpack that. Who is Debbie Leung? How did she end up being such a cornerstone in a field that, let's be honest, can be pretty mind-bending? The sources point out she was born in Canada, showed exceptional talent early on, natural sciences, mathematics, that sort of thing, pursued a double major, physics and math, driven by this deep fascination with fundamental physical principles, things that go beyond everyday understanding, as the essay puts it. And this early curiosity about quantum communication, cryptography, that really set her path, didn't it?
It really did. That path took her to Stanford for her PhD, and there she just dove right into quantum information theory. Her research zeroed in on these core challenges in quantum communication. How do you make it super efficient, but also totally secure?
Right, the efficiency and security. And a big part of that, her doctoral work, involved investigating entanglement. That really bizarre quantum connection where particles get linked, sharing a fate no matter how far apart they are. It's one of quantum mechanics' most, well, enigmatic aspects.
And what's truly remarkable there, I think, is that she wasn't just observing this strange thing. She was figuring out how to quantify its potential, how to measure it. Imagine trying to measure something totally abstract, right? Like the strength of that quantum link. Leung essentially gave us the first reliable way to measure the, let's call it the secret sauce of quantum communication. She developed these theoretical models to optimize how we use this quantum resource. That's the real leap, moving from just asking, what is it, to figuring out how do we harness it efficiently.
Exactly. And she didn't stop there after her PhD. She held major research positions, Perimeter Institute for Theoretical Physics, for example. Then later became a professor at the University of Waterloo's Institute for Quantum Computing, the IQC. And there she did more than just research. She built and led teams, really pushed interdisciplinary work, taught advanced quantum topics, and became a huge mentor for the next generation of quantum scientists. Her ability to explain really complex stuff clearly made her invaluable as an educator.
A real builder of the field.
So building on that, let's dig into how she shaped the practical applications. She wasn't just studying quantum mechanics, she was developing the essential tools for our quantum future. Her expertise covers a few critical areas, but maybe let's start with securing communication quantum cryptography.
Yeah, that's a huge one. She became a leading expert there, quantum communication, quantum cryptography, specifically designing protocols for communication paths that are basically eavesdropping proof. Think of it like creating a communication channel that, in principle, just cannot be hacked.
And a key contribution there was her really rigorous analysis of the security of quantum key distribution protocols, QKD, like the famous BB84 protocol.
Yes, and what's so important is that she didn't just describe BB84 and others. She actually examined how real-world factors like disturbances and error rates affect them. She defined the security limits of these systems. Before her work, unhackable was mostly theoretical, right? A nice idea. She turned it into an engineering problem. She defined exactly how much noise a channel could handle before the quantum security guarantee breaks down. That was vital. It moved QKD from just a concept to something you could actually try to build in the real world with huge implications for data security, privacy, everything.
Okay, so securing the communication. But then there's the challenge of protecting the quantum information itself, which brings us to quantum memory and error correction. These are absolutely critical if we ever want scalable, reliable quantum computers or communication systems. Because as you said, quantum states are just incredibly fragile.
Extremely fragile, yeah.
So Leung's role here involved optimizing algorithms, making it possible to store quantum information without errors, hopefully over longer periods. She developed models to boost stability using these advanced error correction codes. Because the qubits, the basic building blocks, they're just so easily disturbed by, well, almost anything.
That's a great analogy. It's like trying to keep perfect snowflakes intact in a warm room.
Yeah.
That's the kind of interference quantum systems face. So the big question is, how do you keep that delicate information safe? Her work, particularly contributions related to codes like the Shor code, is all about building these incredibly robust, redundant systems for protecting that fragile information. It's about shielding the qubits from environmental noise, basically making quantum computing actually feasible. It's a huge step towards building large-scale, fault-tolerant quantum machines.
And her innovation kept going. She also made really key contributions to other quantum protocols, like quantum teleportation.
Ah, yes, teleportation always captures the imagination.
Right. But it's not beaming people around, of course. It's about transmitting the state of a qubit over a distance without physically moving the original qubit. Entanglement makes this possible. And she developed new protocols to make this process much more efficient and robust, especially in actual experiments, proving it could work in complex setups like optical networks.
Making it practical, essentially.
Exactly. And another defining thing about her career, the sources really emphasize this, is collaboration. Her interdisciplinary approach. She actively worked with computer scientists, engineers, experimental physicists, all sorts. This let her develop these hybrid systems, integrating classical and quantum parts, using the strengths of both to improve efficiency and scalability.
Yeah, and if you're trying to understand how these abstract quantum ideas actually become real-world tools, that collaborative piece is absolutely key. It's her sort of unique talent for bridging that gap between theory and practice and bringing different experts together. That's what makes her work not just academically interesting, but vital for actually advancing quantum tech.
So Debbie Leung's influence really goes way beyond academic papers, doesn't it? Her work has fundamentally shaped the science, yes, but also how quantum tech interacts with our world. It's a story of real impact.
Definitely.
Let's look at that bridge between academia and industry. Her theoretical models, her protocols, they're not just concepts. There's the foundation for loads of innovations. For example, her work on QKD systems. It directly helped companies like ID Quantique and Toshiba develop secure communication solutions. And these aren't just prototypes. They're being used now in critical areas, banking, government.
Real-world security.
Exactly. And her work on quantum memory and error correction, that's directly accelerated the development of quantum computers, the kind needed for really complex calculations in, say, drug discovery, new materials, tough optimization problems.
Her ability to create theories that are not just testable in labs but actually implementable in technology is quite remarkable. That skill, bridging abstract ideas with practical uses, is what makes quantum tech accessible and valuable to industries, to people trying to solve really hard problems. It's essential for moving something from a scientific curiosity to a tool that tackles urgent challenges.
And it's not just about the tech now. It's also profoundly about building the future talent pipeline. As a professor at IQC in Waterloo, she was known not just for her science, but for being an inspiring teacher, supervised numerous PhDs, postdocs, many of whom are now leading researchers themselves all over the world in quantum tech.
Yeah, she didn't just teach the subject, she actively shaped the future workforce, developed key teaching materials, passionately encouraged young people, especially women and underrepresented groups, to get into STEM careers. I mean, her own story overcoming these incredibly complex scientific hurdles with persistence and creativity, that itself is a powerful example for aspiring scientists.
hmm And her work also carries significant weight societally, politically even. Her research on secure quantum communication. It has huge implications for national defense, for finance. It's made governments and industries acutely aware of the need for truly secure data.
It forces people to think about future vulnerabilities.
Right. And beyond that, she played a key role in just making quantum tech more understandable to the public, organized lectures, public events, helping demystify this complex science by explaining it clearly. And she consistently championed international collaboration, stressing how necessary it is to advance quantum tech globally for everyone's benefit.
That outreach is so important for a field like this.
So even with all these amazing breakthroughs, quantum technology still faces big hurdles. How does Debbie Leung's work help address these current challenges and maybe point towards future directions? We should acknowledge the obstacles.
Absolutely. Technologically, scalability and stability are still major issues. Qubits are just so sensitive, needing precise control, super stable environments. Building large-scale quantum computers or reliable quantum memories is incredibly hard. Then there are still theoretical questions. Even with all the progress, we still don't fully understand everything about entanglement or the dynamics of these open quantum systems that interact with their environment. Those gaps can slow things down. And let's be real, the financial side is tough. High costs for specialized gear and the ongoing challenge of proving long-term economic benefits to justify that massive investment.
Leung's approach to these challenges is really a model for the whole field, though. Her strategy was always to develop theories that were directly applicable to practical problems. She actively fostered that interdisciplinary work and was really effective at communicating the societal and economic relevance of her research to get that crucial funding from governments, from industry.
Making the case, essentially.
Exactly. And that problem-solving mindset directly shapes where things are going. We're looking at developing even more robust, more efficient error correction codes for those large-scale quantum computers. Her work also inspires ongoing efforts in hybrid systems, plugging quantum tech into existing classical systems to get the best of both worlds. And for communication, there's a clear path towards global quantum networks, building secure links across continents using those optimized entanglement resources she studied.
Her vision really does provide a roadmap, doesn't it, for tackling these huge challenges and realizing the full potential of quantum tech. It's about guiding us towards an era where quantum capabilities aren't just theoretical possibilities, but tangible, impactful tools across so many sectors: medicine, material science, AI.
So as we wrap up our deep dive today, it's just abundantly clear that Debbie Leung's work isn't merely a chapter in quantum history. It really is a blueprint for its future. She genuinely connects that deep, abstract science to solving global challenges. Her vision of interdisciplinary, practice-focused science is still such an inspiring guide for everyone in the field. We really hope this exploration, drawing on Yorgo Schnepp's insightful essay, has maybe illuminated a path forward for you.
Yeah, hopefully spark some curiosity.
So what will you explore next in the quantum realm, now that you're armed with this knowledge? Until next time, goodbye. And you can find more fascinating insights into quantum technology, including the work we discussed today, over at schnepp.de.